Hello everyone, I'm Bhrigurishi Mishra, PhD student at IIT Bombay, and this is the online session of Elements of Solar Energy Conversion week 8. So in this session I'll talk about the solar air heaters, and I'll solve couple of examples. The other topic, concentrating collectors, will be covered by uh, Mr. Pawan in tomorrow's online session at the same time, 6 to 7 p.m. So there are two type of solar air heaters which has been discussed in the lecture. One is the simple solar air heater, conventional solar air heater, where we have an absorber plate, and then we have a bottom plate. Okay, and the heat is circulated between these two, absorber plate and bottom plate, and then again the typical cover plate, we have to reduce the radiation losses and all. Okay, this is the uh, picture of operational solar air heater. So you can see this is the pump which blows the air to this solar air heater, and then it is collected somewhere here, I guess. Okay, and then this one is the fin type solar air heater. So we have fin here, usually made of steels. Okay, to enhance the absorbing as well as heat transfer property of the solar air heater. So generally this fin based solar air heaters performed better compared to conventional solar air heaters, these kind of, and this we will see in this example. So here we have considered two numericals, where one we will uh, analyze the performance of a conventional solar air heater. uh, just a minute, some network issue is happening. Hello. Yeah, sorry, there was some internet fault. Okay, so we'll start the first numerical problem. So the question is, calculate the performance of a conventional solar air heater with the following data. Okay, so all the data for collector, absorber, plate has been given here. Okay, so we'll start calculating. So we need to like calculate the performance of a conventional solar air heater. Okay, so for the performance, what are the things which we need to calculate? So we need to calculate the output temperature of air. We need to calculate the instantaneous efficiency. Okay, and we can also calculate the pressure drop. Okay, so for this we need to calculate the HFE, heat transfer coefficient between fluid and plate, that means air and plate, HFB, HR, radiative heat transfer coefficient, HE, overall heat transfer coefficient, heat removal factor, FR. Okay, so these things we need to calculate. So first we will calculate HFP and HFB. Okay, so here now we need to assume the air properties, okay, to calculate HFP and HFB. So here the air inlet temperature is given as 50 degrees centigrade. So we need to take the air properties at a median temperature. Okay, so we can assume the mean temperature of air is 55 degrees centigrade, and on that we can use the air properties on that temperature to solve this question. Okay, so assuming that the mean temperature of air, that is TFM, is 55 degrees centigrade. So the properties of air are following. So density rho equals to 1.077 kilogram per meter cube. Specific heat capacity at constant pressure, that means Cp, equals to 1.005 kilojoule per kilogram per Kelvin. Then dynamic viscosity, mu is 19.85 into 10 to the power minus 6 Newton second per meter square, and thermal conductivity K equals to 0.0287 watt per meter Kelvin. Okay, so we'll start with the calculation of HFP and HFB. So first we need to calculate the Reynolds number. Okay, so Reynolds number RE is given as rho V dE by mu. So we know rho and mu. We need to calculate V, which is the air velocity, and dE, the equivalent diameter of the duct. Okay, so equivalent diameter of the duct dE can be calculated as 4 into cross section of duct divided by weighted parameter. Okay, so cross section of duct. So here you can see the dimensions of the duct has been given. So it is, the width of observer plate is 1, okay, and the spacing is 1.5. so that means, so it will be 1.5. okay, so yeah, it is, so cross section of duct is 4 into 1 into 0.015 divided by 2 into 1 plus 0.015, so it is 0.0296 meter. Okay, so now we can calculate the average air velocity, which is V. So V is can calculate using flow rate by area into density. Okay, so flow rate by area into density. Flow rate is here flow rate is given m dot given as 200 kilogram per hour. Okay, area is again 1 into 0.015 into the density. So density we have calculated, we have given here 1.077. So if you calculate it, it turns out 3.439 meter per second. I think there is one 1.5 centimeter, fine. Okay, so this is 1 into 0.015 because so it is given in centimeters. So if you convert it into meter, since the width of absorptive time considering in meter, so that is why it is here 0.015. okay, so we have dE, we have V, and now we can calculate the Reynolds number RE. So equals to 1.077 into 3.439 into 0.0296 divided by 19.85 into 10 to the power minus 6, and it turns out 5515. So if Reynolds value is in between 1000 and 10,000, so that means heat flow is turbulent and fully developed. Okay, so we can use the Nusselt number formula 0.015158 RE to the power 0.8, and if you put RE value of this, we'll get the Nusselt number equals to 15.56. okay, so now here one assumption we need to consider, that the HFP and HFB, that means the coefficient between plate and air and between bottom plate and air is equal. Okay, so assuming this is a fair assumption because both have similar material, and since air is also flowing and the gap is not very high, so we can consider this assumption. Okay, so assuming HFP equals to HFB, so which is Nusselt number into thermal conductivity of air divided by the diameter, okay, the equivalent diameter. So if you solve, we have all the values, 15.56 into 0.0287 divided by 0.0296, so it turns out 15.08 watt per meter square per Kelvin. Okay, so we can calculate now radiative heat transfer coefficient, which is HR equals to sigma by 1 by epsilon P plus 1 by epsilon B minus 1, and TPM plus TBM into TPM square plus TBM square. Again, we don't have the value of TPM and TBM, so we can assume that TPM and TBM are at mean fluid temperature. That means for this case we can consider TPM and TBM equal to TFM. okay, so that means it is equal to mean fluid temperature. Why we are considering this is because the temperature difference between TPM and TBM is not very high. It will be the temperature between TPM and TFM. Okay, so TPM minus TFM or TBM minus TFM is not very high, and it is of the order of 10 Kelvin, and since here we are considering the absolute temperatures, so we can consider that TPM equals to TBM equals to TFM. Okay, and this is a very fair assumption. So if we put this value here, the HR will be, so sigma is 5.67 into 10⁻⁸, and this is 4, since it is twice and here twice, so 4 into 273.2 plus 55 cube divided by 1 by, so epsilon P, epsilon B both are given, both have the same permittivity, same emissivity, 0.95. okay, so it is 1.95 plus 1 by 0.95 minus 1. If you solve this, you'll get 7.24 watt per meter square per Kelvin. So now we can calculate the overall heat transfer coefficient, which is HE. So HE is nothing but HFP plus HR HFB by HR plus HFB. So here HFP and HFP and HFB both are same, so it is 15.08, which we have calculated here. Okay, yeah, here 15.08, so it is 15.08 plus 7.24, HR is 7.24 into 15.08 divided by 7.24 plus 15.08. So if you solve this, you will get 19.97 watt per meter square per Kelvin. Okay, so we have HEHR. Now we can calculate the collector efficiency factor, heat removal factor, and the output temperature. Okay, and the useful heat gain, means the performance parameters of solar air heater. So we'll start with the collector efficiency factor, F dash, it is 1 plus UL by HE inverse, and it is 1 plus UT plus UB by HE inverse. Now UT and UB are given here. UB is 0.8 and UT is 6.2. okay, so we can put these values. So it turns out 1 plus 7 by 19.97 inverse. So F dash is 0.74. So now we can calculate the heat removal factor. Collector heat removal factor, FR is m dot Cp by UL AP 1 minus exponential of minus F dash UL AP by m dot Cp, basically the inverse of this term here. Okay, so first we can calculate m dot Cp. So m dot cp by ul apm dot we need to take care of the sign because units, because some are in kilogram per hour, some are in meter per second. Okay, so we need to take care of this thing. So 200, so this is in kilogram per hour, so converting it into gram per second, 200 1.005 into 1000 divided by 7 into AP, area of the absorber plate, which is given here dimensions 1 and 2. Okay, L1 L2, so AP is nothing but L1 into L2, so it is 1 into 2 and the value of this is 3.988. okay, so thus if you put value of this m dot cp and f dash in fr, you will get fr equals to 0.675. so from this we can calculate useful heat gain, and it is QU, and which is the formula is FRAP. With this we have already studied in the flat plate collector session. So QU equals to FRAP IT into tau alpha average minus UL, okay, UL into TFI minus TA. So we have given all the values. FR we have calculated here. AP is 1 into 2. IT and tau alpha is given. So IT is 950. Tau alpha average is 0.85. And the product of this IT into tau alpha will give you the S. Okay, the heat absorbed by the absorber plate. And TFI is also given. TFI is 50. Okay, and TA ambient temperature 20. so all the values has been given, we just need to put and solve. So if we solve this, we will get QU equals to 866.6 watt. okay, sorry, not 866, it is 806.6 watt. okay, this is the value which we will get. Now what we need to calculate is the instantaneous efficiency. Instantaneous efficiency eta I is QU by IT into AC. Here AC is the area of collector, which is given this length of collector and width of collector. Okay, this will give you AC, this will give you AP. So we have calculated QU, which is 806.6. IT is given 950. AC is also given 1.1 into 2.1. so it is 0.368. that means efficiency is 36.8%. okay, now we have to calculate the output temperature. So from energy balance, m dot cp TFO minus TFI equals to QU. so again considering the units, 200 by 3600 into 1.005 TFO minus 50 equals to 806.6 divided by 1000. so the output temperature is 64.5 degrees centigrade. that means so the inlet temperature is 50 and the output is 64.45 degrees centigrade. so 14.5 degrees centigrade absolute increase. in the temperature, which is quite good. Okay, now we need to calculate the pressure drop across the collector. Delta P is 4F rho L1 V square by 2D, and we can also put the F expression. F expression is 4 into 0.079 Reynolds number to the power minus 0.25 into rho L1 V square by 2D. We have all the values. If we put the answer is 15.78 Newton per meter square. Okay, so here we need to remember these two important quantities. First one is the efficiency and the output temperature, TF. Okay, so the next example is the same question with the longitudinal fins. Okay, so we will check the effect of fins, okay, on the same air heater. So this is the question. So again, considering the same air heater and assuming the following additional data: center to center distance between fins, that means W, fin height 1.3 centimeter, that means LF, and fin thickness 0.3 centimeter, that means delta F. Also we have we are considering it that the fins are steel, so the thermal conductivity K is 50, okay, watt per meter Kelvin, watt per meter square per Kelvin. Okay, so we need to calculate the air outlet temperature and instantaneous efficiency, and we will compare this with the conventional air heater. Okay, one thing is also given which is so given the heat transfer coefficients HFP, HFF, that means fin to fin, and HFB is given as 23.02 watt per meter square per Kelvin. Okay, so we can calculate fin effectiveness. Okay, although in this example these values have been calculated, okay, like again you have to assume the air temperature, since for this case we have assumed that the mean air temperature is 55 degrees centigrade, and we have seen that the outlet temperature is 64.45. so for this case we need to assume higher mean temperature, since longitudinal fins have been fixed. So we can assume 60 degree mean air temperature, and in that basis we can again consider the air properties, and then the same procedure. However, for the fins cases, the formula to calculate Reynolds Nusselt numbers are different. Okay, but we are not going into that detail, so that is why I have considered that HFP, HFF and HFV values are given, okay, for this question, which is 23.02, but it can be calculated, and in this question it is calculated, okay, based on some empirical and formulas. So I'm taking these values as a given quantity and then calculating the further parameters required to calculate these two quantities. Okay, so first one is the fin effectiveness. It is as phi is tan h mlf by mlf. So here m is root 2 hff by kf delta f. So since we have assumed that the longitudinal fins are made of steel, and steel has the K value 50 watt per meter per Kelvin, 50 watt per meter per Kelvin. So we'll use that value to calculate M. Okay, so M is 2 into 23.02 by Kf 50 and delta F is given 0.3 centimeter. So again for the unit we need to convert it into meter. So if you solve, you will get 17.515. so now we can calculate the phi. Again, tan hyperbola e to the power 2x plus 1 by e to the power 2x minus 1, can use that formula, so minus 1 by plus 1, yeah, to calculate this phi. So it is tan h. Now the product of this m into LF, LF is given as 1.3. if you do the calculation, it is and again it is in centimeter, so if you convert it into meter, so the product will be 0.2277 divided by 0.2277, so it comes out 0.9830. okay, then effective heat transfer coefficient, so H equals to HFP 1 plus 2 LF QF HFF by W HFP plus HR HFP by HR plus HFB. So the formula for the longitudinal fins, formula of effective heat transfer coefficient for longitudinal fins is different compared to the conventional fins. Okay, sorry, conventional solar air heaters. So if we put all the values, HFP is 23.02, 1 plus 2 into 1.3 into 10 to the power minus 2 into 0.9830. remember we have considered that HFP and HFF are equal, so these two will get cancelled out. So upon W, which is 2.5 into 10 to the power minus 2 plus HR, we have calculated 7.24, HFB 23.02, 7.24 plus 23.02. so if you solve this, it turns out 52.05 watt per meter square per Kelvin. Now after this, all the other parameters like the F dash, heat removal factor FR, okay, all those things can be calculated using the conventional solar air heater formula. So now calculation for the remaining parameters is same as for the conventional solar air heater. Okay, so so we need to calculate the F dash, which is 1 plus UL by HE inverse, which is if you put values 1 plus 7 by 52.05 inverse, you will get 0.8815. okay, now this m dot Cp by ULAP, the coefficient for the heat removal factor. So again 200 by 3600 into 1.005 into 1000 divided by 7 to 1 into 2, it turns out 3.988. okay, so we can calculate the FR equals to 3.988 1 minus exponential of minus 0.8815, that means f dash upon this coefficient, that is 3.988. okay, so if you solve this you will get 0.7909. So now we can calculate the useful heat gain. Useful heat gain QU equals to this FR 0.7909 into the absorber plate area 1 into 2 IT into alpha average, which is the absorbed radiation. So 950 into 0.85 minus overall loss coefficient, that is 7 into the inlet temperature minus ambient temperature 50 minus 20. So this gives QU equals to 945.1 watt. okay, so now you can calculate outlet temperature again using heat balance. That means so m dot Cp TFO minus TFI equals to QU. so this is 200, again converting it into per second, since m dot is given in per hour, kg per hour. So into 1.005 into TFO we need to calculate, and TFI is given as 50. QU we have just calculated 945.1 watt by 1000. okay, so if you solve this you will get TFO equals to 66.93 degrees centigrade. okay, and the efficiency, instantaneous efficiency, eta equals to QU by AC into IT, and QU have calculated 945.1 watt, and AC is again same, AC and IT are same. AC is 2.1 into 1.1, 2.1 into 1.1, and IT is given 950. Solve this, it is 0.431. so eta equals to 43.1%. okay, so if we compare with the conventional, and okay, so this conventional solar air heater, and this is with longitudinal fins. okay, so this is TFO, that means the output temperature, this is eta I, instantaneous efficiency. So in case of this, TFO is 64.45, this is in degree centigrade and this is in percentage, and eta is 36.8%. oops, sorry. So this is in degree centigrade and this is in percentage. Now for with longitudinal fin, TFO is 66.93. and eta is 43.1. okay, so we can see the difference even with the temperature increase of 2 degrees centigrade. okay, around 2.5, around 2.48 degree centigrade temperature increases the efficiency. The absolute increase in efficiency is around 6.3%. okay, so that means with longitudinal fins will have a better performance compared to the conventional solar air heaters. okay, so that means longitudinal fins is better, although I mean it increases the cost, but since it doesn't require any maintenance, it, it's a better investment. okay, so if we talk about solar air heater, since it requires a mass, like a large area and a very high the flow rate and all, so if we want to get a very good amount of air, so it is not a very it is used for the drying of agricultural products and for space heating, but it is not very efficient for that purpose. So that is why it is generally used for the industrial purpose, where the area can be large, the area of the absorber plate can be large, and it can be utilized very efficiently in industries compared to normal like household purpose. okay, so yeah, that's it for today. So thank you very much.